All right, let's get right into it. We're about to unpack one of the most common and, let's be honest, one of the most confusing topics in Java: how collections really behave when things get busy. We're going to decode a crash that pretty much every Java developer has hit, and I'm going to show you why it's not a bug at all, but actually a super important clue for writing safer code.
Yeah, you know this one. That sinking feeling when you see the dreaded concurrent modification exception. It just stops your app dead in its tracks. But what if I told you that crash isn't what you think it is? What if it's actually trying to help you?
That's right, this isn't a bug, it's a feature. It's a deliberately designed warning sign that's there to stop you from accidentally corrupting your data. And today, we're going to figure out exactly what that clue means.
Okay, first up, let's really get into the weeds of this famous exception. The key to understanding it, and this is the part that blows people's minds, is that it can happen even when you only have a single thread running.
So here's the secret. Every array list has this little or hidden counter inside it called a mod count. Now, when you create an iterator to loop over that list, the iterator secretly makes a note of what that counter's number is. But here's the trap. If you modify the list directly while you're in that loop, not using the iterator itself, the list's own counter goes up by 1. The very next time your iterator checks, it sees the mismatch. It basically thinks, whoa, hang on, something changed behind my back. And boom, it throws the exception to stop everything right there.
So that crash actually reveals this deep, fundamental design decision baked right into Java's collections. It's not about there being one right way to do things. It's about two totally different, competing philosophies for how to handle changes while you're in the middle of a loop. And honestly, this image perfectly captures the two big ideas. On one side, you've got fail fast, which I like to call the shouter. Think of it like a traffic cop who sees a dangerous situation, you changing data while you're trying to read it, and just immediately blows the whistle and shouts, "Stop." Its only job is to protect correctness, no matter what. And on the other side, you've got failsafe, the tolerator. This one is way more chill. It kind of says, hey, go ahead, change the original all you want. I'll just work on a copy to stay out of your way. Its main priority is keeping the application running no matter what. And this is the trade-off you absolutely have to understand. Fail fast works on the real live data. Its whole reason for existing is to protect data correctness, so it will crash your app in a heartbeat if the rules are broken. Fail safe, on the other hand, works on a copy or a special kind of view. It allows modifications to happen because your loop is totally isolated from them. Its goal is to protect the app's availability, to keep it from crushing, even if the data it's looking at might be a little out of date. If you remember one thing, make it this. This is the perfect interview-ready summary. Fail fast is all about correctness. It crashes early to prevent mistakes. Fail safe is all about availability. It isolates the loop to keep things running.
But, fail safe isn't just one simple trick. It actually has two very different strategies under the hood for how it avoids those crashes. Let's dive into those right now. The first strategy is what I call the photocopy approach, and the classic example is copy on write array list. The very moment you start to loop over it, Java takes a complete snapshot, a full clone of the entire array. Your loop then safely reads from that photocopy, which is completely frozen in time. Any changes, like adding the number 3 here, happen on a totally new copy. Your loop is completely blind to it. So yes, it's safe, but the data it's seeing is already out of date. But that safety comes at a huge, huge price. This is the performance chop you have to watch out for. Every single time you call add or remove on a copy on write array list, it creates a full clone of the entire array. So if you have a list with 1 million items and you just add one more, you just copied 1 million items. The rule of thumb here is super clear. Only use this when you are reading way, way more than you are writing. This brings us to the second and much more performant fail-safe strategy, the live view. And this is really where concurrent hash map comes into play. Instead of working from a frozen photograph, it's more like you're just looking at traffic passing by through a window. The cars, your data, can show up and disappear while you're watching. You're giving up that perfectly consistent frozen snapshot in exchange for way better performance. So this behavior actually has a formal name. It's called weak consistency. You can think of it as a contract, a deal that Java is making with you. Java guarantees that your loop will be safe, no crashes, no corrupted data. But in return, it makes absolutely zero promises that your loop will see any changes made by other threads while it's running. All right, let's talk about the real star of modern Java concurrency, concurrent hash map. let's unpack how it manages to pull off this incredible balancing act between being both super fast and super safe. This table really tells the whole story of how we got here. First, there was just HashMap, total chaos in a multi-threaded world, not safe at all. Then they gave us synchronized map. It's like a single traffic light for a whole city. It puts one giant lock on the entire map, which makes it safe but painfully slow. And that brings us to the modern solution, concurrent hash map, which is like a multi-lane highway. It uses a clever trick called fine-grained locking, letting lots of threads work at the same time without getting in each other's way. And this visual just makes it all click. A synchronized map is like one huge room with only one door. Everyone has to line up and wait their turn to get in. But a concurrent hash map is like a hotel with tons of small rooms, each with its own separate lock. If thread A is working in room 1 and thread B needs to get into room 16, they don't block each other at all. And that is where its massive performance advantage comes from. So that amazing performance brings us right back to weak consistency. Look at this. We're adding the letter C to the map while we're in the middle of looping over it. So what's the output going to be? Well, the answer is we have no idea. It's totally unpredictable. The loop might finish before it ever sees C, or it might happen to see it. And here's the kicker. Both of those outcomes are considered correct. The huge lesson here is to never write code that depends on seeing a change that happens during a loop. So let's be super clear about the deal Java is making with you when you use a concurrent hash map. It guarantees you will not get a concurrent modification exception, you will not get corrupted data, and you will not get stuck in an infinite loop. But in exchange for all that safety and speed, you get absolutely no promise that your loop will see data that was added by another thread. That's the trade-off.
Okay, so with all these options, all these different trade-offs, how do you actually pick the right tool for the job in your own code? All right, enough theory. Let's make this really practical. Think of this as your guide. The first question you always ask is this going to be touched by more than one thread? If the answer is no, just keep it simple. Use a regular array list or hash map. If yes, then you ask, is it a list or a map? For a list, you got to know if it's mostly reads or if there are a lot of writes. For a map, honestly, you're almost always just going to default to concurrent hash map. The mantra is simple. Choose the simplest collection that makes your code correct, and only then should you start to worry about performance. And believe me, choosing the wrong collection has very real consequences. This is the classic, well, it worked on my machine scenario. Using a plain old array list for some kind of shared cache might seem fine when you're testing with a few users, but it can absolutely crash and burn the second you put it into production and it gets hit by real traffic from multiple threads at once. Okay, we have covered a ton of ground. Let's boil it all down into 4 simple golden rules. Rule number 1, safety is more important than perfect consistency. Concurrent hash map would rather show you slightly old data than crash. 2, snapshot versus live. Remember, some collections are like a frozen photo, while others are like looking at live traffic. 3, fail fast exists to protect correctness by crashing early. And 4, fail safe exists to protect availability by making sure the app keeps running. So if there's one really crucial point to take away from all this, it's this. Most concurrency bugs don't happen because of a simple typo. They happen because of a flawed mental model, because we assume a collection gives us a guarantee, like a perfectly consistent view, that it simply never promised in the first place. And that brings us to the final thought I want to leave you with. Every single collection you use is making a trade-off between safety, performance, and consistency. You almost never get all 3 at once. So the real question you should be asking yourself is this: what trade-offs are hiding, maybe unintentionally, in your own codebase?